Now here's our second example of applying Newton's second law to circular motion. In the first example, we had a horizontal motion. In the second example here, we have a vertical motion. So something's going around in a circle like this, a mass 5 kilograms attached to a string going around a circle of radius 2 meters. What is the tension in the string at the top when, or I should say when the object is at the top, and what is the tension in the string when the object is at the bottom if the object is going around the circle at a constant speed of 6 meters per second? So that's kind of a strange mechanization because normally it would go faster at the bottom and slower at the top. But what if we keep this thing going at a constant speed of 6 meters per second? What would be the tension here and what would be the tension there? So there's two ways of doing that. One of them is to look at it like this. What are all the forces acting on this when it's up here? Well, for one, and let me use a different color, we have the force due to gravity, which is mg. And then we have potentially some tension in the string or the cable or whatever that is, or a bar pulling down on it as well. And those would be the only two forces acting on it. At the bottom here, we can say that we have the force due to gravity, mg, and then the tension, perhaps like this, pulling it in the opposite direction. All right, now, this seems to make a lot of sense. You would say that if this is larger than this, well, maybe not. I'll take that back. Let me backtrack just a little bit. Okay, so if you look at the top portion right here, something seems strange. The only forces acting on the object are down, the weight plus the tension in the string. And so the idea is when you look at that you would expect for this to come crashing down this way instead of going around in a circle like that. But that's not the case at all. What we can do here is we can find out what the centripetal force is required to make it go around in a circle, and that we do know. So the F sub c needed is equal to mv squared over r. So from that we can calculate what the centripetal force is required to keep it going around in a circle. And then we can see if the mg is sufficient to give the centripetal force. If it's not, then we need additional tension to make up for the deficit that the weight of the object does not supply. That's kind of how you want to look at it. So in this case, we have the mass, which is equal to 5 kilogram. The velocity we set was 6 meters per second, and we have to square that, and then we divide that by the radius, which is 2 meters. Let's see here, that's 36 divided by 2, which is 18 times 5, which is 90 newtons. So 90 newtons is the required centripetal force. Now let's find out what the weight of this object is. So in this case we see mg is equal to the mass, which is 5 kilograms, times acceleration due to gravity, which is 9.8 meters per second squared. And you can see then that the weight of the object is 49 newtons, which is not enough to provide the 90 newtons required for this object to stay in a circular path, which means the tension in the string has to make up the deficit. So in this case, what we can say is that the F sub c, the centripetal force, is equal to mg plus the tension in the string. And so we solve this for tension, then we can say the tension is equal to the centripetal force minus mg. So in this case, that would be equal to 90 newtons minus 49 newtons, which is equal to 41 newtons. So the required tension in the string, in this case, is 41 newtons. Using the same logic at the bottom here, we can do the same thing. So this is, of course, at the top. And we do the same at the bottom. And of course, F sub c needed, or required, would be the same thing, right? Going around in a circle with all the parameters the same, radius, mass, and so forth. We know that this is also going to be 90 newtons. Now, the centripetal force is going to be equal to the tension provided by the string minus the mg, minus the weight, because the weight, of course, is pulling in the opposite direction. So what we can say here is that the centripetal force F sub c is equal to the tension minus mg. If we solve this for tension now, we have to move the mg over to the other side. So the tension is equal to the centripetal force plus the mg. So in this case, the centripetal force is 90 newtons. The weight we calculated here is, where did I go? Where's my weight? Right here, 49 newtons, so plus 49 newtons. So that means in this case, we need a centripetal force, or we need a tension of 139 newtons to keep everything going around in a circle. But again, the way the brain reacts is that it has this ability to look at things from a life experience manner, which means that when things go around a circle, we have the impression that things get pushed to the outside, and we have to pull on the inside to keep them from moving to the outside. So if we take that concept here, and we look at the motion at the very top, right there, here's the object, we can say that downward we have a force, which is mg, the weight of the object, and we have the tension in the string, which is pulling down, and outward we have a force called this fictitious centrifugal force, F sub c, which, when this is balanced with this, it keeps things going in a nice circular path. So if we use that concept, we can say that the mg plus the tension in the string is equal to the centrifugal force. In other words, mg plus the tension is equal to mv squared over r, because the equation for the centrifugal force is exactly the same as the equation for the centripetal force. And then you can see that tension is equal to the mv squared over r minus the mg when you put it to the other side, which is the exact same equation that we got right here. Centripetal force equal to this, so the tension is equal to the centripetal force minus mg, or the centrifugal force minus mg. Then at the bottom, when the object is down here, we can do the same thing again. What are all the forces acting on it? Well, we can see that we have the mg, which is pulling downward. We have the tension, which is pulling upward. Let me move over here so it's probably easier to see for you. And then, of course, we have the centrifugal force, which also acts downward to the outside of the circular motion. And then we just set all the forces that act to the outside equal to all the forces that act to the inside, and see what we get. So if we then use that same principle, we can say that the tension to the inside is equal to all the forces acting on the outside, which is mg plus the centrifugal force. And so you can see that this is equal to mg plus mv squared over r, which is exactly the same as what we got over here. The tension is the centripetal force plus the weight, and we get the total amount. So sometimes it's just easier to think of it in terms of there's some fictitious centrifugal force pushing things to the outside, and then there's some forces pushing to the inside. In this case, the weight is also pushing the outside, so all the forces acting on the outside must equal all the forces acting to the inside, and we find the correct answer in that respect as well. So that is how you do a problem like that.